Hello everyone, welcome to the class. In the last lecture, I explained you how we have to design a low pass signal from a band pass signal, and then how the mutual conversion can be done from a low pass equivalent signal to a band pass signal and vice versa. Let us look at the communication system from that perspective again. Now, if you see this diagram explains that we have to first design the low pass signal. That means this signal will be corresponding to the modulating signal, the output coming from the sensor and the source, right? So you design, so that means that will be a low pass signal. But for obvious reasons of the need of modulation, you have to transmit. This is a low frequency signal, so you have to modulate it to a high frequency carrier signal so that you can transmit onto the channel to gain the advantages of modulation. So that process will be called as the upconversion. Upconversion is a process to convert a low pass signal to a band pass signal. So this signal is then transmitted to the channel, and at the receiver side you have to perform the down conversion, because once a high frequency signal is received at the receiver, it is very difficult to design electronics which have to deal with the which has to deal with the high frequency signals. So therefore, we have to bring down the frequency so that we can design low frequency electronics at the receiver end. So that will lead to a less complex as well as a cheap receiver at the receiver side. Now, so then the detection is performed that what was transmitted from the transmitter side. So that will be the output that can be fed to any output device. Now, what we can to model a complete system, what we can think of, because this is a up conversion leads to a band pass signal, channel will be a band pass channel, down conversion will then convert a band pass signal to a low pass signal. So this whole block diagram corresponds to, we can model the whole the channel as well as the up conversion and the down conversion um, as a band pass channel, right? So we can consider it to be a band pass channel, but we can consider channel as low pass, right? Because this whole channel is this whole system which is in this box is actually is actually a band pass channel, right? But we can consider it to be a low pass signal because we know that we can convert a low pass signal, a band pass signal, to a low pass equivalent signal. And we can you will see in this lecture that I will explain how the system or the channel can be, a band pass channel can be converted to a low pass equivalent channel and vice versa. And even the receiver can also be converted into a received signal, can also be converted from a band pass to a low pass equivalent and vice versa. So we model the complete block diagram in this box as low pass and complex. But the task is how to obtain this channel. I mean, how to once we get the low pass equivalent baseband channel, because this is the band pass channel. Now we model this band pass channel as its low pass equivalent baseband channel. The question now is that how to obtain this channel, so that in the model you will see that we are only dealing with the low pass signals, right? So let us see what is this concept. So this is the modulator. I explained you in the previous lecture also how the modulation will be done. So this is the low pass signal. Low pass signal is multiplied with the carrier, right? And then we obtain the band pass signal and we transmit it onto the channel. This is the block diagram of a modulator and complex. And in the previous lecture, I also explained that complex baseband to bandpass conversion. So this is the general. This is the complete block diagram where the baseband to bandpass conversion and then bandpass to complex baseband conversion will be achieved. So this is very important because at the transmitter we will design the baseband signal and convert it to bandpass signal, that is sub conversion, and then transmit to the channel as I have just explained. All right. At the receiver, we will convert the baseband signal back from the bandpass signal and perform further processing of the signal. Right. Now we have to actually look for the complete, as I was trying to explain you in this diagram, uh, uh, this up conversion process, the channel, the down conversion process. So we model the complete block diagram in this box, represented in this block, in this white colored box, as a low pass equivalent baseband channel. So let us see how we can do that. How we can do that? Okay. So equivalent complex baseband representation of band pass systems. So this is, earlier we dealt with the signals. Now since this becomes a system, this is a band pass system, we have to look for the low pass equivalent baseband system now. So we must understand the difference between the signal and the system. So this part is the signal. We have to now deal with the system. We have to look for the low pass equivalent baseband system for a band pass system. Okay. Okay. The equivalent baseband representation of systems is similar to that of signal. So the process that we followed to design the low pass equivalent signals, we will follow the same process except for a few minor differences. So let us see what are those differences. So bandpass system with impulse response HT and transfer function HF is actually this is the impulse response. So if we take the Fourier transform of this, we will get the frequency spectrum or the frequency spectrum of this channel of this impulse response. Okay. So as I explained you in the signals case also, so we have to take the positive side of the spectrum because we are dealing with the band pass system now. So we earlier dealt with band pass signals. Then we took the positive side of the spectrum of the signal. In the same way, we will take the, and that positive side we call as the analytic signal. So in the same way, we will consider the analytic system, which is actually H plus F. That means the positive side of the transfer function of the system, and the impulse response H plus T of the analytic system are respectively defined as H plus F equal to UF HF, right? And because we are multiplying it with the unit step function, so unit step spectrum, so we will only get the positive side. So if we take the inverse Fourier transform, we will get the analytic system, right, which is equivalent to getting the analytic signal. Inverse Fourier transform of H plus F, right? So equivalent baseband system. So we have to, this is the positive side of the, this represents the positive side of the system. Now we have to look for the low pass equivalent of the system. The transfer function HLF, which is the low pass equivalent. That means actually we have to, this system is actually lying on the spectrum is lying on the positive side of the frequency axis. So that means, and the spectrum is not centered at 0, it is centered at a non-zero frequency because it's a bandpass system. We have to bring back this bandpass system we have to bring this bandpass system back to a point where the spectrum will be centered at 0 frequency. So how can we do that? The same process. So we shift the band pass system to a low frequency signal with this process, which is H plus F plus F0. So that means this is the shifting by how much frequency? F naught. So now we want to express the transfer function of the baseband system, which is HLF, in terms of the transfer function of the passband system, which is HF. How can we do that? We have obtained the transfer function of the baseband system. So this is the transfer function of the baseband system. Now we can write it if whatever is the transfer function of the baseband system, we shift it to the right by F naught. So that's what we do here. The transfer function of the baseband system is shifted to the right by F naught. So that means that will be representing one part of the band pass system for F greater than equal to 0. So that means it will be equal to HF. But for F less than 0, this will be 0 because we are only having the base transfer function of the baseband system and we have shifted to the right. But we know from the symmetry relation that HF is equal to H star minus F, that is the conjugate of HF minus F, which holds since HT is real valued. Now we can express the full band pass system in terms of the low pass, the transfer function of the low pass system or the baseband system. So transfer function of the band pass system will be equal to the transfer function of the low pass system on the positive side, and it will also plus HL star minus F naught. So what it represents is basically this term represents the positive side of the transfer function, the spectrum of the transfer function of the band pass system, and this represents the negative side of the spectrum of the band pass system, right? In terms of, so that means the transfer function of the band pass system is expressed in terms of the low pass equivalent transfer functions, right? By HL F minus F naught plus HL star minus F naught. Now, if you take the inverse Fourier transform here, what you will get is inverse Fourier transform of HF will be equal to HT. This will be equal to, since this is the shifting of the transfer function of the baseband system by F naught, so it will have to be multiplied with the time domain transfer function of the baseband system has to be multiplied with e to the power j2 pi F naught t plus HL star. This is on the other side, HL star t e to the power minus j2 pi F naught t. So HT will be equal to this, right? Now we know that HT will be equal to the real part, twice the real part of HLT, and if we expand using the cosine and the sine function, using the Euler's formula, if we expand the e to the power j2 pi F naught t and e to the power minus j2 pi F naught t, then we will see that this HT will remain, HT will be equal to twice of real part of HLT e to the power j2 pi F naught t. So that means what we have done here, we have expressed the band pass system we have expressed the band pass system in terms of the low pass equivalent system using this formula, right? Okay, now we can try to find out whether linear filtering in complex baseband is equivalent to the same operation in the passband. That means if you look at the upper box, what the upper box represents, this is a band pass signal. Band pass signal is passing through the band pass channel, and we are receiving a band pass signal, which is RT. And we have seen that we can express the band pass signal XT in terms of the low pass equivalent signal XLT, and we can recover the band pass signal back from this baseband signal also. Similar operation can be done for the band pass system also. We can express this band pass system in terms of the low pass, the transfer function, the low pass or baseband system, and we can recover the band pass system also. So can we do it for the received signal? So that's a question we have to look for. Um, this is the band pass signal. Can we get the low pass equivalent of the received signal? And we can convert, we can recover back this band pass signal from the low pass equivalent. So if we can do that, that will complete the analysis. Okay. Now this RF, which is the received signal spectrum, this can be obtained by taking the Fourier transform of the RT signal, and we can also express it in terms of the multiplication of the transfer function with the bandpass signal XF, HF, XF. And we have already seen that how we can express HF in terms of the low pass or baseband, the transfer function of the baseband system. Here I have just explained you that the transfer function of the bandpass system can be expressed in terms of the transfer function of the baseband system, bandpass to baseband, the representation of the bandpass system in terms of the baseband or low pass system. So we can express that. So I'm using the same formula here for substituting this HF with HL F minus F naught plus H conjugate L minus F minus F naught. A similar operation can be done for the bandpass signal also, like this, the same operation. And why this half sign is there, we have to do the scaling factor, because when we did the if you, I can show you here, it's here. When we took the positive side of the bandpass signal, we multiply it with 2 because we wanted to keep the energy constant. And so that's why we are using here a scaling factor of 1/2, because just as a scaling factor we are using half. Now if we take the, now you have to multiply these two, sorry, you have to multiply these two terms inside the brackets, so you will get 4 terms. Out of the 4 terms, for 2 terms which I have put it here, XL F minus F naught, HL star minus F minus F naught, and XL star minus F minus F naught, HL of F minus F naught. So ST and HT have narrow band character, so this will be equal to 0. If you take the Fourier transform and represent this thing like this, since ST and HT is a narrow band character, so these 2 terms can be approximated to be equal to 0. And we are left with now this term. And of course, it will be 1 over under root 2. So RF will be equal to only true for 2 terms after multiplication. XL F minus F naught, HL F minus F naught, XL star minus F minus F naught, and HL star minus F minus F naught, because these 2 terms will be equal to 0. All right. Now, if you look at XL F minus F naught and HL F minus F naught, this represents the RL F minus F naught. And if you look at this term, XL star F minus F minus F naught and HL star minus F minus F naught, this actually represents RL star minus F minus F naught. So what we have done here, this is the bandpass received signal. We have been able to express this bandpass received signal in terms of low pass, in terms of equivalent low pass received signal or baseband received signal, right? So that means we can, if we take the inverse Fourier transform. So about the scaling factor, for getting the system, the explanation about the system, we did not multiply it with 2. But for getting the input signal, right, the representation of the bandpass signal and the baseband signal, we multiply it with 2 for getting the positive side of the spectrum. So that's why we are multiplying it with just a scaling factor of 1/2. So when we are multiplying these scaling factors, so individual terms will be multiplied with 1 over under root 2. So that's why this 1 over under root 2 is there. This is only a scaling factor, so nothing to be worried about this. Okay. Now, if you take the inverse Fourier transform, if you will take the inverse Fourier transform of this, you will recover the RT signal back in terms of RLT. So that means your received signal can be expressed as the received bandpass signal can be expressed in terms of the received low pass equivalent signal. So that actually explains this question mark, that we can obtain the low pass equivalent received signal from the bandpass received signal, and we can convert, we can vice versa, we can also perform. Vice versa, we can uh, get the low pass equivalent from bandpass signal or system, and we can also convert. We can also get the other way around also. Right. And now if we take the if we take the if we take the Fourier inverse Fourier transform of RF, then what then inverse Fourier transform of this equation, then what we will get is we will get RT equal to real time of the baseband received signal multiplied by e to the power j2 pi f naught. So this result shows that we can get the output RT of the linear system HT by transforming the output RLT of the equivalent baseband system HLT. And we can do the reverse operation also. So this is an important result since it shows that without loss of generality, we can perform linear filtering operations always in the equivalent baseband domain rather than doing it in the bandpass system. The reasons I have already explained you that for doing the operations in the bandpass system, you require a complex electronics hardware, and the cost will also increase of the systems. So this is very convenient. For example, if you want to simulate a communication system that operates in passband using a computer. So if we bring everything into the baseband domain, then we can do the simulation also, and we can implement the systems cost effectively and with a lot of simplicity, rather than designing a complex system for handling high frequency signals and systems. So thank you very much. I end my lecture here. Thank you.